With him, he brought a Kalashnikov and some armor-piercing rounds.
Soviet problems require Soviet solutions. Today we're going to be looking at Discovering Chernobyl's Elephant's Foot by that Chernobyl guy. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's take a look.
In June of 1986, dosimetrists Mikhail Kostyakov and Vladimir Kabanov found themselves at the foot of a flight of stairs on the ground floor of the destroyed reactor of Chernobyl Unit 4.
So, dosimetrists, these are going to be radiation protection specialists. And yeah, it would make sense for these personnel to be among the first to go in and investigate Unit 4. But compared to, say, the liquidators, which involved a lot of military and, let's just say, not all personnel that were extremely well trained in radiation protection, these individuals were going to be among the best, which makes sense when doing a post-accident assessment.
Investigating something that wasn't quite right. In previous weeks, they had already explored the destroyed remains of the reactor, regarded as among the best on the site. But this had not come without consequences. One day, Kostyakov had walked past an open hatch in the southern pump hall of Reactor 4, when his dosimeter, which could read up to 1,000 rontgens per hour, went off the scale. He continued.
Alright, so unit is rontgens per hour. So a rontgen measures exposure. So think of it as measuring it in terms of ionizations. I mean, after all, this is ionizing radiation that we're talking about. That is not the same thing as absorbed dose, that is. The unit for absorbed dose is going to be rads or grays, where there's 100 rad in 1 gray. And that is energy per unit mass, joules per kilograms. Now, since most measurements are going to be dominated by gammas. 1 Rontgen is approximately 1 rad, which is 0.1 grays, which is approximately 0.1 sieverts. Now, a sievert is biological dose. So you take the raw absorbed dose in grays, joules per kilogram, you multiply it times a quality factor to get sieverts, which that's the one that directly measures the effects on the human body. And for gammas, that quality factor is going to just be 1. So that's why a lot of these people are mentioning Rontgens, and they assume that they're equivalent to 0.1 sieverts. And that's close in the case of a gamma-dominated source, but the multiplication factor when you convert from grays to sieverts goes up depending on what the source of radiation is. Neutrons can be anywhere from 5 to 20 multiplication factor depending on the speed of the neutron. Though those are only a hazard when the reactor is operating. And in internal alpha dose, the quality factor is 20. So it's 20 times worse to ingest an alpha particle. But this sort of distance dose, it's going to be gamma dominant.
Continued on, anyway, completing his tasks, only to find the skin peeling off his leg during his evening meal.
Now, radiation by itself does not cause immediate skin sloughing within hours of exposure, unless it's extremely localized to that particular body part, extremely high, and accompanied by some sort of burn. Now, radiation reddening did occur within hours at Chernobyl, and blistering and necrosis occurred days to weeks later. So there might be something, so it sounds like there's something a bit off in the time frame.
The next day, his superior, Konstantin Chercherov, went to the same open hatch with a more powerful dosimeter and found a radiation level.
I mean, that's the correct thing to do. If your dosimeter is maxed out, you need to find something with a wider range. That's one of the few things that Chernobyl HBO series actually got right, is that when something was maxed out at 3.6 Rontgen per hour, and then they realized they need to get a wider range instrument. That's one of the few things they got right, was the whole principle of maxing out a narrow range instrument.
Of 9,000 rontgens per hour in the vicinity.
In some cases, it was over 9,000.
When he lowered the dosimeter into the space below the hatch, the radiation level approached 11,400 roentgens per hour.
And that makes sense, because you're getting closer and closer to the source.
At radiation levels that high, just standing there for 158 seconds would be enough to prove fatal for half of people exposed to it in just 30 days.
Okay, so he's looking at LD5030 numbers. So that's going to be in the 5 to 6. I don't actually know the LD5030 numbers off the top of my head. I know the LD5060 numbers are going to be between 4 to 6 sieverts, an acute dose of that. So this is going to be a bit more than that, but well below 10. And unconsciousness would occur even faster within maybe a minute or two. And unconsciousness could occur even faster within a minute or two. Now, on very high dose rates like this, the amount of exposure geometry to each individual part of the body and shielding matters a lot. There's going to be a huge difference on the order of centimeters in terms of what that dose rate is. This is one of the reasons why, for certain activities such as sending personnel into steam generators during an outage, there's dosimetry not just placed on the person's chest, but also on the arms and legs of the individual, because the dose rate can vary widely per body part. And there's not just a whole body dose limit, there's also dose limits to an individual body part. Now, the dose rate for that job is nowhere even remotely close to this high, but every slight variation when the numbers are this high is everything.
A month earlier, a fire had broken out in the southern pump hall, and during the efforts to extinguish the blaze, one of the 282 firefighters fell through the hatch and broke his leg.
Ugh.
Other firefighters were able to rescue him using a board and rope, but when
This is a bad location for there to be a fire and radiological accident.
those firefighters handed
Like there's ever a good location for that, but you know what I mean.
in their radiation levels, they were refused leave from the exclusion zone because their superiors didn't believe the radiation dose they had recorded.
Wow.
None
That's horrible.
of their fates were documented. Such was life in the zone.
So a lot of these dosimeters were frequently overranged or improperly calibrated and just saturated to the point where people just straight up did not believe their detectors. That's horrible. That means you need to get better detectors. So the assumptions were that the instruments were failing, which is a systemic failure at the highest level, because this is about personnel safety.
Now, Kostyukov and Kabanov stood in the impossible. Despite being on the ground floor, their dosimeters read 25 roentgens per hour. The very bottom of the reactor was roughly 4 floors above them, and more than 25 meters away, not to mention all the shielding from the walls of corridors between them. There had to be a very powerful source of radiation at the top of those stairs.
So yes, there's quite a bit of shielding. There's concrete, there's steel, there's pipes with water in them. All of these are pretty effective at attenuating gammas. And there is actually quite a difference between some corridors versus other corridors into the dose rates experienced within them. And kind of going back to why a lot of the dose rates were unbelievable, because a lot of people thought the dosimetry was broken, or the radiation detectors were broken, is the radiation fields within Unit 4 at this time were very chaotic. Because, as I'm sure he's going to get to soon, it wasn't just the elephant's foot. The elephant's foot was a big concentration, but there's bits and pieces of fuel fragments everywhere. There is a variance in the thickness of the concrete shielding and all the varied lines of sight. There's all these. Some of the corridors were designed to have dog legs and a bit of a tortuous path to further attenuate gammas. So one potential step could increase dose rate by orders of magnitude. And you can see how this could quickly lead someone to believe that the dosimeters were wrong because of that much variability. But this is what radiation transport physics looks like post-accident in a destroyed structure. It's not pretty at all. And it's entirely possible and because of this, a lot of the dismissal of the radiation detection wasn't malice. It was just people just didn't know the severity of the situation, or that radiation fields could vary by that much, where every step counted.
Armed with a Kazach 3 dosimeter, designed from extendable rods that could measure up to 3,000 rontgens per hour, they slowly raised the dosimeter up the flight of stairs. As it passed 3 meters up into the floors above, the number kept going up. And then, on the second floor, floor plus 6.0, the dosimeter immediately went off the scale and broke. Whatever was in room 2...
Yes. So, ionization chambers can oversaturate, Geiger tubes can quench, and even the cables that are in the electronics can degrade under high dose.
217-2 on floor plus 6, just 2 floors above them, was so radioactive that they lacked the means to measure it. They never went up the stairs to go look for themselves. Because why? It was far too dangerous for no good reason.
Well, that at least is the correct decision to do when your detector overranges, to stop and not go that way.
And that decision probably saved their lives. Because we now know what is in room 217-2.
Because that's what's just as scary, isn't just that it's high, but you're effectively blind going in there if your detector's broke. The correct response when a detector malfunctions is to immediately head in the opposite direction, notify radiation protection or additional radiation protection, since these personnel are radiation protection, and get another dosimeter and put yourself in a safe, low-dose area.
The elephant's foot. And while they didn't know it, they had become the first people on the planet to document its existence. Months would pass, the sarcophagus would be built, and concrete would be poured into the structure to stabilize it. The dosimeter that Kostyakov and Kabanov used would be trapped in the concrete forever, as the 2 workers left it when the device stopped working.
That's good. Anything that could potentially over-encumber you when essentially evacuating from a dose limit, from getting an unexpected source of high dose. Yeah.
Attention had turned from building the protective shelter over the structure to actually assessing what happened to the fuel within. There were 2 primary concerns. The first was the structure of the fuel, and if it could go critical again. Sustained nuclear fission requires a fuel, which in an RBMK is fissile uranium-235, and a moderator.
So yeah, and that's a fair concern. You want to be absolutely sure that the fuel is separated enough, or what's left of it, and there's no way a critical geometry could form to essentially start another self-sustaining fission reactor. That is the most important critical safety function in a nuclear power plant when you're in your emergency procedures, is subcriticality. It's actually more important than keeping the core, or core remnants in this case, cool. Because after all, you're going to struggle to do that with emergency core cooling system if you have not shut down your reactor. And the reactor is shut down, but part of that is measuring dose to verify that it's still shut down, or really measuring neutron dose.
Graphite in an RBMK. Neutrons are slowed down by the graphite, increasing the chance of a successful collision with another uranium-235 atom, producing more neutrons and continuing the chain reaction. In a nuclear reactor, this could be controlled through many means, all of which were lost when the reactor was destroyed. But if the fuel and moderator remained close enough, and in a favourable ratio for nuclear fission, then they would be in a lot of trouble.
Yes. Now, the odds of something like that happening with the core in a destroyed state like this is pretty low, but the consequences for something like that is pretty high.
The second concern about the fuel was, well, where was it? The reactor had been supposedly burning for days, and during that time helicopters had been used to dump boron, dolomite, sand, anything that might have been useful to smother the blaze in the reactor hull. Of those 5,020 tons, the Soviets knew most of it could never have made it into the core, not only because they were doing it by helicopter in runs, but also as the upper biological shield of the reactor was covering the entrance to the shaft,
Yeah.
making it near impossible to access. There's also the possibility they were aiming for the wrong thing altogether, but that is a story for a different time. The point is that they didn't know if the fuel was still in the reactor shaft, or if some of it had escaped into the building somewhere. It should have been easy to simply walk through those corridors and examine everything just by following the floor plans. But the hasty efforts to stabilise the structure had turned Chernobyl into effectively a cave system.
Yeah, and dose rates are going to be extremely high and variable in all of these corridors. So, man, trying to make a decision like this in what areas to survey and investigate where you have incomplete information and the building is unrecognizable, that's extremely difficult to say the least. I mean, one of the things that you're trained on, that nuclear engineers and operators are trained on, is having to make decisions with incomplete information. But here, since all your indicators were essentially destroyed, that is to say your remote indicators and instrumentation that you would monitor from the control room are destroyed, man, that's just horrible and miserable from trying to even make a decision with said limited information about what to do.
With open chambers like the reactor hall, and tight crawl spaces where concrete filled floors up almost to the ceiling. This was no easy space to explore. Special teams and preparation would need to be made for it. Radiation levels were high, and the first plans involved sending robots into those dangerous areas. Unfortunately, these robots proved completely useless. In one demonstration, recorded for the sarcophagus explorers to witness, a specially designed robot was placed in one of the corridors of the sarcophagus, where radiation levels increased the further down the corridor one traversed. The robot drove forward down the corridor some 6 meters to its first obstacle, a metal pipe about 12 centimeters in diameter. The robot stopped, unable to cross the obstacle.
Yep.
2 workers had to help it over. Entering the high radiation zone, and the robot only made it another 1.5 meters before it stopped again. The operator couldn't bring the robot back to life, and again the 2 workers had to run over and bring it back. But still, the robot would not respond to the controller, causing the operator to just give up. 2 minutes later, the machine turned itself back on, spun around, and charged at full speed down the corridor, clearing the 12 centimeter pipe, clearing all the obstacles to the very end. And finally, wheels making a grinding noise, it gave out, toppling over onto one side. Lots of cursing ended the tape, to which the Government Commission simply asked if the robot had been retrieved. It had, never to work again. It appeared as if robots would never be usable at Chernobyl, not just because of radiation, but because of terrible designs.
Yes, I'm glad he pointed that out, because, yes, some electronics did fail due to high dose, but a lot of these robot failures were mechanical problems. I mean, Soviet robotics in 1986 were not the most maneuverable, not the most hardened, and not the most reliable. In a lot of cases, the motors were undersized for what the robots were supposed to be able to do and maneuver.
They needed something small, something mobile, and something simple that could traverse the alien terrain. Enter the toy tank from Children's World. About the size of a telephone, it was perfect for the conditions. The cable was lengthened,
Telephone back
and
then, I'm sure.
dosimeters, thermometers, and a flashlight were attached on top. And from there, renamed Microbe, the toy tank went, able to scan corridors and determine the radiation levels before the sarcophagus workers got there.
I mean, that's the way to do it. Something simple with minimal electronics and short mission durations. with the limited technology you had back then, that's definitely one of the better and underappreciated designs there.
It was quickly decontaminated and sent out for the next mission. Eventually, in spring of 1987, this robot became too dirty to be decontaminated.
Sure.
And was buried inside the sarcophagus.
And that's what happens with a lot of radiological tools. You reach a point where, yes, they can be decontaminated most of the time, but eventually the contamination just gets too internal, and it could be to the point where it would just be, you'd just be better off making a new one than the cost of decontaminating and taking every individual part off, deconning, and then putting it all back together. In some cases, it's cheaper to build a new one.
If you want to learn more about this little tank, I strongly recommend Chernobyl Family's video, Rebuilding the Device.
Cool.
It's a really interesting project, and his channel, in general, is very, very interesting. All this work was good, but it was getting them no closer to finding any of the fuel. The toy tank could not by itself traverse the cave network of the sarcophagus. Only people could. This is where Vasya Koyagin enters the story. Koyagin, a speleologist who wound up caving through the concrete-filled levels of the sarcophagus, was obsessed with the bottom of the reactor, which was held up by a 100-ton steel cross. What happened to the room the cross was in was unknown, with some people theorising that perhaps even a hole had formed in the lower biological shield, the steel and serpentine plate under the reactor, something many never considered, as they thought it was too extreme. Nobody knew for certain, and Koyagin wanted to find a door to the room.
Yet another issue with not having a proper containment structure, that a proper external containment structure in addition to biological shielding around this reactor design. Because that includes on top and below and around the sides, just an external reactor containment structure, capable of withstanding the entire energy of the reactor system.
To crawl underneath the cross and assess what happened. An absolutely crazy idea, considering if there was a hole, the radiation levels could have given him a fatal dose in seconds.
So one other thing I wanted to point out about these fatal doses within seconds. It doesn't mean death within seconds. It's considerably worse. You'll experience nausea and dizziness within seconds, loss of consciousness within minutes, and death would take days to weeks. I mean, you'd reach that threshold within seconds, potentially, for these very high dose fields. Radiation destroys bone marrow, destroys GI lining, and causes vascular collapse and lots of internal bleeding. So yeah, it's worse.
But that was never going to deter him, and frankly his superior, Vladimir Asmolov, was not deterred either. While consulting the floor plans, Koyagin managed to find his route to the heart of the disaster. It's actually quite simple, really, as there was a staircase that would take him to that very corridor. This was staircase 257. From there, all he had to do was walk south down corridor 301/6, enter the big door on his right to corridor 318/2, and then the first door on his left would take him straight to the reactor hall.
Let's see if the remains of the Chernobyl reactor core respected this floor plan.
It's that simple. And so, in December of 1986, he set off. He descended the staircase, passing by corridors blocked off by concrete flows, and then made his way to the floor he anticipated the door to be on. Here, the concrete flows and formations had created a passage he had to traverse by crawling, flashlight in one hand, dosimeter in the other. Radiation levels were quite low compared to some values we've encountered earlier.
Sure.
Just 10 to 15 roentgens. But then the number rapidly rose, and Koyagin had to duck into an adjacent doorway. This room was quite hot, but the radiation level was just 1 roentgen per hour. He was safe here. When he
hot temperature-wise, not radiation-wise, interesting.
Peeked into the corridor, down at the end was a large mass of something. He didn't know what it was, but he knew that whatever it was It was the source of the radiation.
You don't want to walk close enough to find out, I'll tell you that much.
To understand Koyugin's next moves here, we need to mention the inverse square law.
Yeah.
Something that you might not have necessarily come across before. In essence, the inverse square law describes that the intensity of something physically quantifiable, such as light, sound, or in this case gamma radiation, is inversely proportional to the distance from the source squared.
Yes, I regularly bring this up as a great rule of thumb a lot of my videos, so this is definitely good that he's pointing this out.
So, if for example, you're 1 meter away from a gamma source and your dosimeter measures 4 roentgens per hour, if you moved just 1 meter away, you would measure 1 roentgen per hour. If you moved another meter away, you would measure 4/9 of a roentgen per hour. You can see how quickly it drops off. But the same is true in reverse.
Yeah,
and that
you get
radiation
closer, it
would
goes
quickly
up.
ramp up. So, Koyugin approaches the pile.
Now, here's the thing, and yes, this is a great rule of thumb for back-of-the-envelope calculations, this inverse square law, and as I said, I use it all the time for these videos. Here's the problem with it, though. The key assumption, and he showed it on his little graphic that he did with the light source, it assumes a point source, which in most cases is good, or at least good enough, because there's a lot of hot particles, hot spots, hot sources during when you do radiological surveys. That approximation is indeed accurate, or at least close enough, or close in a conservative way. That is indeed acceptable. However, the inverse square law has some limitations. I already mentioned point sources. Another one is in open geometry. This is a mess of a building, and this thing is not at all uniform. And without scattering. There are all kinds of things mentioned, the steel piping, water in pipes, concrete, a lot of things that can increase the probability of scattering. Because this thing is extended, it is within reflective concrete, so you're going to get a lot of gamma scattering. And this is from the Compton effect. So, unfortunately, it's not going to be as accurate as they thought. And, of course, just by looking at it, you can't really tell, can you? Because you don't know the composition of this mass. So, that is to say, how much is a radiation source, how much is a scatterer, how much is a absorber, and how much literally does nothing with regards to gamma radiation. So, when dealing with an unknown source, an unknown uneven source with unknown uneven numbers of ways that it can interact with other material, the inverse square law is not going to be the most accurate thing. So, what do? Well, just like anything else, time, distance, and shielding. Do not be anywhere near this thing for longer than you absolutely need to be. Still keep your distance. It might not be a precise inverse square relationship, but being further away from this thing is still going to be good for you. And use shielding. Having concrete between you and that is a good idea.
Measuring the radiation, and from here he can only guess what the level will be when he gets up close and personal with the mass. Now, he didn't have a floor plan on him, so he couldn't get a good sense of how far from the mass he was. But if he was right, behind it was the magical doorway he wanted to find. Estimating his distance to the mass to be 20 meters, and using the dose he was reading right there, about 50 roentgens per hour, he estimated that the mass was putting out no more than 20,000 roentgens per hour. If he spent 30 seconds running down to see if the door was there, he'd be fine. And so he did, running up to and past the deadly object, as his dosimeter went off the scale. Unfortunately, his magical doorway was absent. There was only a stairwell leading downwards. So he calmly made his way back out the corridor.
There you go. That's the right thing. When you're in an unexpected situation like that, just go back. It's like, oh, I guess I didn't have the shielding that I planned for.
Through the tight passageways, and back the way he came out the building. When he told this story to his boss, Vladimir Asmolov, he simply couldn't believe how crazy the story was. It would take them 25 days to finally get an estimate of the radiation dose around the elephant's foot. Some 8 to 10,000 roentgens per hour. Koryagin had overestimated his distance from the mass, and his radiation estimate had been off by half. It transpired that he'd been on the wrong floor.
Glad he was wrong in that he overestimated. That is a good type of wrong to be, rather than the alternative.
The entrance to the bottom of the reactor shaft he was looking for was above him. Not that it mattered anyway. That route was rendered inaccessible due to a concrete flow that almost entirely filled the corridor, and therefore he couldn't get in through the stairs. But they had no idea what Koryagin had come across. Their initial assumption, based on its black glossy texture, was that they had discovered the molten lead that had been dropped by helicopter, but they couldn't say for certain. They needed photos, and they needed samples.
And you know what? That is a fair assumption based on what they knew at the time. After all, lead was dropped, but I don't know if they knew how little of it had actually reached the core. But if it was lead, it would have vaporized, oxidized, or flowed elsewhere or something. Because lead melts at a little over 300 degrees, whereas this corium monstrosity was over 2,000. That's 2,000 Celsius.
The first man to descend in there to capture a photo of the mass, then dubbed the cone, was Valentin Obodzinski, a veteran of the Soviet nuclear industry who had already dodged death in another nuclear accident. After taking this
Seems to be a common theme for personnel involved in this particular accident. Yeah.
photo, the government commission ordered they take more. But at that point Obodzinski had been relieved from the site, having received such a significant dose at Chernobyl, on top of his exposure in the previous accident, that any more expeditions into the sarcophagus could prove life-threatening.
And that is a real thing that's still done today. Now, granted, nobody gets that much dose today in the industry, but there are lifetime dose limits within the US. So people that do the job, like the steam generator jumpers that I mentioned earlier, you can only do that so many times. And keep in mind, all dose rates are kept below 50 millisieverts per year, and the dose where an increased risk of cancer is evident is twice that at 100 millisieverts per year. But there's still a more conservative lifetime dose rate that is a function of your age. That is more conservative than that, as in to say smaller than 50 millisieverts times your age.
Obodzinski was sent back to Moscow for treatment, and years later he would lose one of his legs to his long-standing radiation dose. In his place, Moscow sent a photographer that not only had never stepped foot in the sarcophagus, but had never stepped a single foot in the exclusion zone before. And on the first day on the job, he was sent with a rare high-quality...
How about that? Your first job at Chernobyl, and you're going to go take a picture of the elephant's foot.
Japanese camera through the tight, cramped spaces to take high-quality colour photographs of the cone.
Good luck. By the way, if you ever need someone that absolutely needed a radiation protection escort, it would be the sort of person that did not have the extensive experience. And in today's world, he would have gone through at least some level of radiation protection training, so he knows all the warning signs, even though he would indeed be escorted for this sort of high radiological job. I don't know if that's what took place here, but anyway.
Him was an absent-minded dosimetrist who was supposed to ensure he didn't get too close to it and immediately send himself straight back to Moscow for treatment.
Well, I guess that answers my question. Okay.
While many of the other workers waited in the decontaminated, so-called clean room, the absent-minded dosimetrist returned and struck up a conversation with some of the other workers. Just then, the lights cut out. This wasn't unusual, as work on the sarcophagus continued, and people were hurrying to get everything finished for the holidays.
Yeah, it's not a good thing to have an absent-minded radiation protection expert that's supposed to be providing escort.
One of the workers noticed this man had not changed from his dirty or contaminated shoes when he entered the clean room, and he was quite audibly reminded of his error.
That's, basic radiation protection fundamentals.
By the other people on his shift. But then another worker, Alexander Borovoy, spoke up, asking one simple question. What have you managed to photograph? The dosimetrist turned white as a sheet. I led him, he said, to the room on the right, the hot room with the small dose, crept for the additional searchlight, came back to the fellows, chattered, and quite forgot, that he is there, below. He is waiting.
Wow.
Can't get out himself. I want you to picture yourself as this photographer. It's your first day on the job,
Yep.
and you are brought through a network of confusing, tight passages and enter an unbearably hot room, where you are told to wait. And, after several minutes, the lights shut out. Silence. You have no idea what's going on. No sense of direction. Nothing but the heat in the room. An unbearable heat that seeks only to push you out to find somewhere cooler.
That's nothing short of terrifying. Also in the back of your mind, assuming I'm a person that I might have heard of what radiation is, but I don't fully understand the hazard or anything, and no, that's around the corner too. Heat and radiation in the dark. Yeah, that's horrifying.
And this somewhere cooler, not through the tight crawl spaces, but down this corridor. And without realizing, and without warning, that cooler air has led you right in front of the radioactive mass you were sent to photograph.
Does he have an active dosimeter that's going to start to alarm?
Where in just a short time, you will receive a lethal dose of radiation. Such was the scenario unfolding in the mind of Borovoy and many of the others in that room. Before many of them could leave the room, the photographer appeared at the end of the corridor. He'd fortunately decided to make his way back out before the lights shut off. When he saw one of those would-be saviours, he beat him over the head with his camera. A lucky miss. The sarcophagus operative group gathered that evening in their hostel and laboratory, a converted gynecological department in the municipal hospital of the town of Chernobyl. The tiled walls made it easy to decontaminate, and all the furniture was made from stainless steel. That night, the debrief ended with only one person speaking up about the forgetful dosimetrist. Let him go. We won't work with the person who forgot about his colleague.
Yeah.
And so it was. The dosimetrist was removed from the sarcophagus.
Good.
The photographer had a long career at the site, with the dosimetrists often having to stop him from becoming too obsessed with collecting the right pictures and walking into a high-dose zone, or holding him as he dangled out a helicopter to collect the perfect angle of a photograph of the roof. So, now they had photos. The next task was collecting a sample. They tried everything in doing so. The first attempt was made by Old Faithful, Microbe, the toy tank. The robot was further modified to attach a drill to the structure, and it was slowly sent out to attack the elephant's foot. Unfortunately, the drill could not generate enough axial force to crack the surface of the foot, owing to the lightweight design of Microbe. The device was recalled, and it became apparent that humans would have to go in to collect the samples. The next attempt was made by the military. Not with scientist permission, mind you. But a brave officer nonetheless attempted to smash the elephant's foot with a fire axe.
Wow.
This also failed to significantly damage the structure, and the officer was dismissed from the sarcophagus for exceeding his radiation dose.
You don't say, yeah, you're gonna exceed your dose limit with a fraction of a second at this point. Not receive a lethal dose, but exceed any reasonable dose limit.
But something had broken off the surface amidst all these attempts, and they were finally able to bring some of the mass back to their laboratory for analysis. There was no lead, so everyone finally agreed the lead dropped on the reactor previously was useless, but the composition was very unique. It seemed to be a porous glass-like structure formed from the sand that surrounded the reactor before the explosion, mixed with concrete, zirconium, steel, serpentine, and, of course, the fuel and its decay products.
So, and this will illustrate, so what it actually is it is a molten silicate glass matrix. And the hottest substance here was indeed the nuclear fuel, not just radiation in terms of temperature, because it melts at over 2800 C. The zircaloy cladding melts at 1800-ish, and concrete decomposes in the 1500 range. So that's what you get. Embedded fuel particles, and all these fission products are trapped here heterogenously.
You might be surprised to hear that the fuel only accounts for 5 to 9% of its mass.
That's a good thing. That means the uranium was widely dispersed. So all concerns of criticality, extremely unlikely. This will mean the neutron mean free path is very short since it's going to be embedded within the silicate. In other words, the geometry was horrible for sustaining any sort of fission reaction. So no, you're not going to get criticality. After all, in order to sustain a fission reaction, you need sufficient fissile mass, a good moderator, favorable geometry, low neutron leakage, and no dominant absorbers. So this elephant's foot had dispersed fuel, no geometry, no organized geometry, I should say, no graphite moderator, very high neutron leakage, and you had all these absorbers seep in. And even if water were to seep in, because water is a moderator, the moderation would be localized and transient, and ultimately just not enough of a source of positive reactivity. And again, it was hot. The steam voids would disperse it. So at this point, their concern should be alleviated of that.
At least in the elephant's foot. And it is far from the highest fuel content of all the subsequently discovered lava masses. So, mystery solved. The cone, as it was still called, was not going to go critical without warning, as there was no moderator. Job done, right? No. One day, someone had an idea to collect more samples from deep within the mass. There was concern once more that the mass could go critical. If there was some moderator inside, in an appropriate configuration, combined with water that was seeping its way into the sarcophagus, then they were back on for a criticality.
Again, it would take a lot, but at this point they haven't really quantified everything yet, so sure.
Oh dear. In another meeting in the gynecology ward, the manager of the entire group immediately refused to send more people in to get pointlessly irradiated trying to smash up the corium. Across many evenings, they tried to come up with a solution to their problem, when someone said they could just shoot it and collect the
this
shrapnel.
is when this happens.
So they asked the military for a gun. The military sent them to the police. The police sent them to the KGB. And the KGB sent them to the police again. Fortunately,
This sounds about right.
a sniper worked at the police at the time. One Captain Soroko. With him, he brought a Kalashnikov and some armor-piercing rounds.
Soviet problems require Soviet solutions. And yeah, this is up there.
And then they descended into the tight network of corridors and gullies to shoot the monster in the corner. It turns out that their sniper may have been too good. All 30 rounds were shot at their targets. And they found the mass to be made of several distinct layers that would, quote, peel off, end quote, after every round. After they were done, a significant chunk of the lower portion of the mass was blown off, and the top of it, where it had poured down from the ceiling, was shattered completely, permanently ruining the so-called beauty of the elephant's foot. But they got their samples. There was no...
There you have it, your tactical sampling device. In case you're wondering, even armor-piercing rounds cannot reliably penetrate nuclear fuel. But they're good at knocking off brittle silicate layers, which is where they got this information from.
Appropriate fuel moderator ratio, concentration, or configuration, let alone pretty much any moderator in the material at all. And therefore, no risk of another criticality. The elephant's foot had enlightened the workers on the nature of the disaster, that at least some of the fuel had escaped the reactor core. Now they had to find the rest of it. From thermal measurements taken in the hot room near the elephant's foot, it appeared that there was a large heat source directly under where the reactor was. That cross that Vasya Koygin had been looking for when he discovered the elephant's foot. Again, however, the risk of sending people to look into these areas was considered far too high. After several deliberations, one physicist...
I'm glad they're at least appreciating the high risk at this point, despite earlier talking about instrument failure because your device overrange. But then again, at this point, a lot more experts are looking at it.
Spartak Balayev pushed for boring holes through the concrete walls of the destroyed reactor into the vessel itself, and then inserting probes to analyze the situation. At the end of 1987, the complex expedition team was formed. At its head was Alexander Borovoy, who had been managing the tight relations between the government commission, headed by Boris Shabina, and those who had to work in the challenging environment of the sarcophagus. This team was dedicated to the drilling operation. Several rooms were decontaminated, and the drilling began at the start of the new year, slowly to minimise the risk of kicking up dust. Some were designed to penetrate the lower concrete pad underneath the cross, to assess if the meltdown had in fact damaged the structural integrity of the reactor itself. Others were drilled into the upper levels to assess the contents of the reactor shaft. As mentioned before, the risk of graphite and uranium in a configuration that could go critical was the greatest threat, and one that many expected to see.
Interesting, a lot of people expecting to see that. It just goes to show you the poor design at work here, even continuing to bite you post-accident. Because, at least at the nuclear power plant that I worked at, while subcriticality is the greatest critical safety function, there weren't a whole lot of realistic scenarios that involved a post-accident restart on this type of scale. Mainly just because restarting a destroyed reactor like this, is just not remotely possible. But I guess in the case of this specific design, there could be a magic geometry that somehow gets you there. I mean, after all, the great joke is AZ-5 did shut down the reactor by tearing it into pieces and placing the bits and pieces of nuclear fuel far enough away from each other that it would not restart.
First of these to break through into the reactor region was from the top of room 207-5, entering the concrete pad underneath the cross. On May 1st, 1988, Workers' Day, a public holiday in the USSR, members of the complex expedition were celebrating into the late night when Borovoy received a call from the sarcophagus. It was the boring team, and something was going wrong.
I thought it was going to be the boring team, and then something got interesting. I love his presentation style, by the way. It's pretty good.
Beamy fog was coming out of the borehole being drilled into the concrete pad beneath the reactor cross. Borovoy ordered everyone to immediately leave and seal the doors to form a hermetic seal, while he looked for any drivers to take him to the site that weren't intoxicated from the festivities. When he arrived, Borovoy met up with the drillers, and then descended on his own down to the drill site, where he encountered one of the guards who had stayed at his post for the past 5 or so minutes, while the fog had engulfed him. Officially, the guard...
So, yeah, what caused this, it's not a restart or recriticality, it's decay heat, and it's still a lot. So, immediately after shutdown, and I guess in this case, the accident when the reactor was destroyed, it maintains about 6-7% of power, and that rate goes down logarithmically. But even months later at this point, the decay heat from the fission products is still going to be on the order of a few kilowatts per ton, which is enough to cause flashing of water that comes into contact with, which can aerosolize radioisotopes and potentially cause an internal dose hazard.
Todd couldn't leave his post without dismissal from a superior, so Borovoy scared him out of Unit 4 by telling him if he stayed 10 more minutes, he wouldn't have to leave. They could just bury him on the site at that point.
Wow.
Once the situation was assessed,
Yeah.
Borovoy and the drillers used a series of hoses to spray down the dust from the fog to the ground, and then wash it away.
Yeah, the dust being the key hazard here. You do not want to breathe that in, because internal doses are not only potentially much higher, especially if they're alpha particles, hence the whole times 20 quality factor, but they're also difficult to remove, decontaminate, because they're in your body now. Now you have to take into consideration the half-life of the isotope and then your biological half-life, how long it's going to remain within your body before your body excretes it. And that all depends on what it is.
So ended the mining operation into the concrete pad under the reactor. The drilling experiment confirmed that an enormous amount of the fuel had ended up in this room underneath and melted down into the concrete, generating an immense amount of heat from radioactive decay.
Yes.
When the water that was used to cool the drill flowed into this hole and encountered the hot, decaying fuel, it heated into steam that rapidly decomposed the material into a dust, which was then blown out of the hole. The next day, the drilling team were able to penetrate into 305-2.
And that's why later efforts, such as the new safe confinement structure, focused on creating a new confinement structure to cover the aging sarcophagus. And the strategy there is one on isolation as opposed to cooling.
The room where the cross should have been. Except for one problem. There was no cross. The entire lower biological shield had descended down through it, either during the explosion or during the meltdown, with the fuel melting the steel cross until it could no longer hold up the weight of everything above it. Late on the night of May 3rd, 1988, the drilling team pushed through into the reactor shaft. By their estimates, if the reactor had dropped 4 meters, the centre of the reactor should have been there. People took bets on what they would find, but the general assumptions remained the same. The graphite stack still present in the core, and some melted fuel rods. A probe was placed into the hole, so they could measure the size of the active zone they were dealing with. Because it was late at night, and people were tired, nobody paid much attention when the probe reached the other side of the reactor, until they were on the bus heading back to the gynecology laboratory, of course, and then a mixed feeling of confusion and amazement took over. Another, larger hole was drilled into the side of the reactor, this time so a camera could be inserted into the gap. When they went in, their suspicions were confirmed. The reactor was in fact empty of fuel.
That's a good thing. It means the fuel was physically expelled and relocated during the accident, so that there was absolutely no way you can have a critical geometry or even a critical mass.
All of it was either ejected in the explosion or escaped out the bottom of the reactor, along with all but a small amount of the graphite. This was perhaps the best news the scientists could have received, as now they could confidently say there was no risk of a potential criticality given the low chance of the appropriate fuel moderator configuration forming from the ruins. Of course, they still had to find the rest of the fuel. The inside of the core they did find was unique for a different reason. Not for what it didn't contain, but what it did. Several concrete panels from the reactor hull, of all places, were found in the core, along with some of the insulation that surrounded the steam separators. Somehow, these had been blown inwards during the explosion, before Yelena crashed back down on top of them. This would suggest that at least that region of the core was devoid of fuel and graphite in the few seconds after the explosion.
So what this also proves is the explosion was a mechanical steam-driven explosion. And again, this is going to shift the long-term risk of the Chernobyl site to contamination rather than criticality. And this influenced a lot of severe accident modeling procedures. And that would include how you assess core damage and model severe accidents. This also led to hydrogen mitigation systems such as recombiners to prevent hydrogen from forming a volatile mass.
I'll let you be the judge of that. The elephant's foot was first made public in an article in the Pravda magazine on December 8, 1989. Alongside it was the first published photograph of its untouched appearance. And from there, images slowly began to trickle their way into the public, birthing stories of a Medusa, and instant death, and mirrors to photograph it. But
Nah, nothing is instant, but sure. I mean, stories are gonna flow along with lots of misconceptions.
the continuation of the story of the elephant's foot is for another day. And finally, I want to discuss one photo that seems to have caused controversy. I am, of course, talking about
this one.
the ghostly figure seeming to stand and walk around the elephant. Some people have wrongly claimed that this was the first photo taken of the foot. It's easy to prove this is not the case, as the top of the elephant's foot has been blown off in this photograph. As you may know, the person in the photograph, as well as the photographer,
not actually a ghost,
is Artur Korniev, but it was in 1996, some 10 years after the disaster. He had no role in the shooting, let alone being the man who shot it, as some have claimed. As always with the Chernobyl disaster, the more you learn, the deeper and more mysterious the story goes.
In case you're curious if this elephant's foot could be recreated in a modern reactor, well, no. RBMKs have specific vulnerabilities like the positive void coefficient, the graphite moderator, the lack of containment in the case of Chernobyl, and a massive core with no melt retention. Compare that to the reactor that I worked at, which had a negative temperature coefficient, a proper containment structure, hydrogen recombiners, and passive decay heat, and safety systems that could not be defeated during any form of testing while the reactor is online. This was a very well done video. I can see why everyone has recommended this channel so much. I really enjoyed watching this one. Thanks so much. I'll see you next time.